This
with
conference will now be recorded.
So the presenter in the 2-minute papers, he comes up with the latest technologies and gives a 2-minute introduction to every latest technology out there. So I definitely recommend the first 3 channels. You should subscribe to top 3 channels and check them out at your own convenience. Now, I hope everyone knows who these 3 guys are. So if you're aware of them, you can unmute yourself and tell me who these guys are. For those of you who are working in the area of machine learning and AI, I hope you know who these guys are, or at least one of them. Anyone? You can unmute yourself and I will not be able to look at the chats, but if you can unmute yourself and anyone? That's all right. So these 3 people are actually the godfathers of AI. I think you must be aware of the Turing Award that is given to the pioneers in the area of computer science. So in 2019 March, these 3 people, they were awarded the ACM Turing Award for their contributions to the field of deep learning. So these guys are Yoshua Bengio, who's on the left. So he's a professor at a prominent university in Canada. I think it's University of Montreal. Then the person in the middle is Geoffrey Hinton, who is responsible for the most famous algorithm, backpropagation in neural networks. He also, he and his student also developed quite a few of applications that are used in the deep learning field today. And the person on the right is Jan LeCun. So Jan LeCun is actually right now a chief scientist at Facebook. So he is actually very famous for this architecture, which is known as LINET. So when LINET, came into existence in around 1998, that was when deep learning started getting attention. So these 3 guys, deserve a lot of respect and recognition, and they got, deservedly the Turing Award in 2018, in March 2019, but the year was 2018, for the year 2018. Now, let's begin with what is artificial intelligence. Now, people, when they talk about artificial intelligence, so the very first question that comes to their mind is, what do you mean by artificial intelligence? Is it that machine which is behaving intelligently? Can I say that that machine is, smart enough to behave like humans? So such questions, they coincide with the fact that, for example, let's say you must be using artificial intelligence every day, even if you don't know it, like when you use music recommender systems, Google Maps, Uber, or other applications, they are like powered with AI. However, I already told you before, like there is this huge confusion between the terms AI, ML, and DL. So even I would say a popular Google search, if you look at, is like how artificial intelligence and machine learning, how they differ. So the term artificial intelligence actually came into inception in around 1950s by a group of researchers, Herbert A. Simon and John McCarthy. He is one of the person that you're seeing in the slide is actually one of the fathers of AI. So nowadays, if we look at, human AI interaction gadgets like Google Home, Siri, Alexa, and these machine learning powered like video prediction systems, which power Netflix, even Amazon and YouTube. So the advancements that you see, they are actually progressively becoming essential in our daily lives. So whenever we talk about artificial intelligent agents. So they are, you could say, they are intelligent assistants that enhance our abilities as, I should say, humans and professionals. They make us more and more productive. So, uh, so you could say that a machine is intelligent, or it has artificial intelligence, when it can actually gather information about its environment and make smart decisions based on that information that it has gathered, or based on the knowledge it has gathered. So then I could say that that machine has enough artificial intelligence. Now the next question comes is, how would you know that a machine is like truly artificial intelligent? So this test, which is very famous in even the theory of computation domain, which is known as the Turing test, it was actually designed by Alan Turing in around, I think, 1950, where the goal is to test the machine's ability to exhibit intelligent behavior, which is equivalent to, or you could say, indistinguishable from that of a human. So Turing actually proposed that a human evaluator, he would judge these natural language conversations between a human and a machine, which is designed to generate human-like responses. So if the machine can actually fool the evaluator, then you could say that the machine is intelligent enough. So this test is actually, I mean, I would say not a good measure, but I mean, a good starting point to prove that if machines are intelligent enough or not. Now, what is actually machine learning? So now, if I define machine learning, then you could say that I want to automate a certain task by the use of machines. So basically, this discipline employs actually various algorithms to teach computers to accomplish tasks where no fully satisfactory algorithm is available. What I mean to say is, so suppose if I ask you to simply compute, say, what is the interest that you will gain on your savings? So then, because I know the direct formula, so there machine learning is not required. However, if there are tasks, like if I ask you, if I give you an image and ask you which is the digit present in that given image, so then writing a, you can say, a code to figure out what is the digit present in that image is a complex task, because it is hard to define those characteristics which make up a digit. So we'll discuss what kind of tasks we could want to do with machine learning. So this machine learning field actually tries to automatically improve, say, a system's performance by making use of existing data that is out there. It also deals with the fundamental laws that govern the learning processes. So we'll discuss everything in detail as we move forward. So the idea is, we are given a training set and we want to learn a model built on this sample to build using this sample data, and we want to make predictions or decisions without being explicitly programmed. So so as we move on, the definitions would become more clear, and on what kind of tasks we would want to do machine learning, and where we would employ traditional programming. I mean, these would be more clearer as we move forward. Now, how this machine learning is actually different from DL. Even DL is a part of your, I mean, you could say deep learning is also a subset of machine learning, but deep learning deals with neural network architectures. So the idea is, in machine learning, you come up with some handcrafted features. For example, in this say in this slide out there, I want to identify whether in a given image I have a car or not. So I can manually handcraft certain features, like whether it has two circular ovals or not. So they could represent tires. Now I could also say that based on this shape of this vehicle. So if cars, they follow a certain streamlined shape, so I can characterize this shape as a certain feature. So in any given image, if I see these characteristics, so I can tell that if a car is present in this image or not. So what I did was I handcrafted certain features, and based on those feature values, so the machine learning model will characterize whether if it's a car or not. Now in deep learning, it is slightly different. You don't need to handcraft the features by yourself. So the features are learned implicitly. So what you will do is you will directly feed in the image, and the model, or you can say the deep learning architecture, will figure out if it's a car or not. So for every image, you will simply provide whether there is a car inside it or not, and the deep learning model itself will figure out certain features. Now these features could be say whether some circles were present or not, whether certain shapes for windows were there or not. So even though these features are implicit, so the deep learning model is responsible for feature extraction and the classification part. So this is how deep learning is different from ML. Even when we could also differentiate deep learning in other aspects from traditional ML. Now, deep learning has I would say, a very fascinating, I mean, a background theory behind it. So with deep learning, suppose, I would say that when you do learning with a lot of labeled images, so there you would observe that. So I'm just going to make a chart. Sorry, uh, pardon me, just 1 second. So I'm going to make a chart. Oh, I'm really sorry. So I'm going to make a small chart here. So the x-axis actually represents the amount of data that you feed to a model. Now it could be a traditional machine learning model, or it could be a deep learning based model. Now it is observed that as you feed in more data to a deep learning model, and on the y-axis I represent, you can say, the performance of this model. So if you feed in more amount of data, the performance actually increases with the amount of data, that you fed to the model. Now it has been observed that with deep learning, this performance never plateaus. Basically, this will keep on increasing. If you have more data, if you can capture more information in your data set, this performance will keep on increasing. However, when you talk about traditional models, so there the performance with a small amount of data, it is better than these deep learning models. However, the performance tends to plateau even if you provide a large amount of data beneath a certain threshold. So if you look at this graph, it tells you that this green line, which is representing traditional machine learning algorithms, they tend to plateau. Their performance tends to plateau even if you feed them more data. So that is one interesting thing about deep learning, is that if you have more data, you could actually be doing, you can actually improve as you get more data. However, that is not the case with traditional machine learning algorithms. So that's the reason, one of the reasons I would say machine learning is actually very popular nowadays. Now, there are other factors on which you can actually differentiate deep learning with machine learning. One of the factors is when you talk about, because deep learning has a lot of, or I would say a large number of parameters to estimate, in comparison to your traditional machine learning models. So they depend on, I would say, high-end machines, contrary to the traditional machine learning algorithms, which can even work on your desktops and low-end machines. So now, nowadays, everybody is working with GPUs. So GPUs are essentially used to do these matrix multiplication operations in the deep learning context. So these operations, I mean, these matrix multiplication operations nowadays, they can be actually efficiently optimized, and they can be done in parallel. So that's why, I mean, NVIDIA GPUs are getting so popular nowadays, and everybody is moving towards this deep learning. Earlier, we didn't have this, I mean, capability of executing so many operations in parallel. But I mean, with the hardware, I would say advancements, this is becoming possible. Even to, I would say, even to access more data and even to analyze more data with GPUs. Now, another thing that is different when we talk about machine learning and deep learning is that, so in traditional machine learning algorithms, basically the problem is actually broken down into several parts, and then these solutions to those individual parts, they are combined to get the result. But deep learning, however, it tries to solve the problem from end to end. So for example, let's say you are doing a multi-object detection. So in a image, there are, say, multiple objects, and you also want to identify what those objects are. So if you were doing, say, a typical machine learning model, then what you would do is you would divide this problem into two parts. So the first part would be like object detection. So there you would try to draw, or you can say identify, a bounding box across those objects. I mean, so you would try to delineate a boundary to identify where those objects are in that given image. And after you have identified those, after you have identified those, the boundaries across, you can say, surrounding those objects, then you can actually recognize those objects using any recognition algorithm like support vector machines, or like logistic regression or decision trees. On the contrary, say, if you do deep learning, then what you would do is you would have a single model which would do everything from end to end. So for example, if you're aware of this YOLO architecture, so there you pass an image in just one single step, and it will actually tell you the location of that image, as well as what is that particular, what are the particular objects that are present in that image. Now, another factor I can say is that which is different across these two domains is that deep learning algorithms, they take a lot of time to train. Actually a lot. So a very popular architecture or deep learning model that you would have heard of, the residual network architecture, or more commonly known as ResNet, it actually takes more than 2 weeks to train. Completely from scratch. However, these classical models, they take, a few seconds or maybe a few hours to train. However, but when you want to do predictions, so these deep learning algorithms take very much less time to run in comparison to certain classical algorithms like k nearest neighbors. We will discuss what these algorithms are, but the idea is, deep learning models, they take a large amount of time to train. However, when you do testing, when you do predictions, it takes a very small amount. Another thing that differentiates deep learning with machine learning is that you could say interpretability of these algorithms is one of the factors that you can keep in mind. For example, say you are giving say handwritten essays as an input to a deep learning model, and you want to give say some scoring to these essays. So basically, you're feeding in a handwritten essay, and you want to print a score, say, out of 10. So if you just simply build a deep learning model, the results are quite excellent, and they actually match, I would say, near human performance. However, there is an issue. The issue is it actually does not reveal why it has given that score. The interpretability of deep learning models, so far, I would say, even researchers are now working on it. The field is known as explainable AI. So there, it is very hard to determine why is it that this score was awarded. So the interpretability of these models is not good enough. On the other hand, if you talk about, say, models like decision trees, they would give you crisp rules like why they chose a particular score for deciding. They would tell you that this article was written well enough, if it captures certain topics brilliantly. So a deep learning model is, in fact, I would say, not a good interpretable model as compared to like other machine learning algorithms out there. Now, when we talk about, deep neural networks, or especially neural networks, so you would want to know what are, what are neural nets. So a neural net is actually, you could say, a logical structure which is similar to how your brain works. So you could say that we represent our world, or whatever we see, as a nested hierarchy of concepts. So for example, in the image on the right hand side, I want to identify which is the individual in that given image. So this particular image is of George Washington. So suppose I was to so my goal was to predict, if I give you an image of presidents, you have to tell me which president is there in that given image. So now the first thing that we would look at is like the color of hair, how the eyes are there, the shape of the nose, the shape of the lips, certain facial characteristics. So all these characteristics, basically, they can be, you can say, characterized as certain concepts, like the edges can be combined to make, say, more complex figures like eyes and nose. And these, different, you can say, components, they make up the whole face. So the idea is each face can be broken down into sub-modular concepts, like individual components like nose, eyes, and lips. Similarly, these nose, eyes, and lips, they are made up of several edges, several shapes. So this hierarchy that we are trying to learn, this nested hierarchy, is what this deep learning architecture is trying to learn. So if I summarize the architecture, it says that the deep learning models, they actually use a layered architecture, and this layered architecture is actually representing the world with a nested hierarchy of concepts. So when we talk about deep neural networks, in comparison to you can say a vanilla neural network where we have only one hidden layer. So this one hidden layer is actually trying to learn either the edges or a more complex feature like nose and eyes. So when we talk about deep neural networks, you could imagine that there are tons of these layers. There are several layers within a network, and with these individual layers, we are trying to identify these concepts in a nested hierarchical manner. So that is how these neural networks work. Now, just to give you an idea of how deep learning has developed over the years. So, so the very first thing, the very first architecture of a neuron, which came out in around 1940 by McClintock and Pitts. So they defined the architecture of a neuron, where they said that neuron interprets some signals based on a certain threshold. So if an input is exceeding a certain threshold, the neuron gets activated. Otherwise, it is not activated. It will not pass that information through that input. Then in 1950, Frank Rosenblatt came up with the architecture of a perceptron, a basic perceptron. And in the next decade, around 1960, Adeline, which is nothing but the implementation of, you would say, the hardware implementation of the first perceptron model by Widrow and Hoff came out. And the field of machine learning and AI, it started gaining traction. Now, from 1960 to 1970, it was considered to be as the golden age, where there was a lot of research in that age. However, in 1970, a paper by Marvin Minsky and Seymour Papert, they actually proved that these neural networks are not even sufficient to model a XOR problem. So with that, I would say that the assertions went down, and people they started to disassociate themselves with AI. So for almost 2 decades, I mean that in that period, no funding was there. People started to work in other areas. So that period was called as the dark age of AI, also known as AI winter. In around 1990, the person that you see in the middle, Jeffrey Hinton. So yeah, he came up with the, efficient. So one problem with training these networks was you would have to come up with a large amount of data, and there was no efficient way of solving the optimization problem of neural nets. So then Geoffrey Hinton came up with the backpropagation algorithm, which is used till date to train, larger neural nets. So then it again started picking up pace from there. Another important development was by Vapnik and Cortez in 2000. So they built the support vector machine model by using the maximum margin principle. So there, with SVMs, the popularity grew, and it grew so much that SVM became so popular that they were used in almost every other application. Very recently, not almost like 2 decades back, closer to, I would say, in 2005, Jan LeCun, who's a recent ACM Turing Award winner, close to 2005, he came up with several neural network architectures where he showed that that the performance actually matches to human performance. So again, machine learning gained a lot of attention, and then this, I would say, deep neural networks came into the picture. And very recently, in 2010, the concept of transfer learning became very popular. It was popularized by Hinton and Ruslan. So they said that you could use pre-initialized neural network for training. For training for a new data set, and the convergence would be achieved much quicker than if you were training it from scratch. Another, I would say, a milestone, which is not there in this particular figure, was achieved in close to 2015. So this architecture came out, which is known as Generative Adversarial Network, or GAN. So I would say in the last decade, from 2010 and 2020 to 2020, it is the, I would say, the best development which was done in the field of AI. And now there are several variants of GAN out there. So I would show you certain applications of GANs. And the applications are actually very mesmerizing. So you would be actually fascinated by those applications the imagination you would see in the subsequent slides. It is very fascinating. If you are into deep learning research, a few key things to note is that across the years, there have come out, several neural network architectures. Now, these architectures, they differ in terms of the number of hidden layers. So more the number of hidden layers, more is the number of parameters. So here I have shown you a few of those architectures. The circle, you could say the radius of the circle is actually representing the number of parameters that the model requires to train. And on the y-axis, it is representing the accuracy on the ImageNet dataset. ImageNet dataset is actually a standard dataset which has like 1,000 classes. So you have 1,000 different categories like bear, swan. So you want to have differentiate between, say, different objects. So there are like 1,000 different categories in that particular dataset. And these are the performances, performances corresponding to the different neural network architectures out there. So I would say, if you look at this particular figure, so the performance of Inception V4 stands, the top. So the corresponding to this light blue circle, corresponding to Inception V4, you have the best performance. and even it requires a very lesser number of parameters. Now there is another model which is known as efficient net, the one in black that you see. This model requires the least amount of parameters, but it is still achieving, a reasonable enough performance. Now, if you have, say, a very limited GPU memory, so nowadays, to train these huge networks, you require a large amount of GPU memory. So, because some of these models take even weeks to train, so you would require, more than 2, or I would say 4 to 8 graphic cards to train them. For very big models like exception, inception, and they have like more than I would say more than even 150 layers. So to train such models, you need a large amount of parameters and a large amount of GPU as well. Now the idea is, if you were teaching deep learning to your I would say to your students, and you would want to implement a deep learning project, then you would want to know how well will I be able to do if I have, say, if I know a specific amount of parameters or a specific model if I take. So the idea is, if you look at this figure, so it shows you the performance of the different models, and these performance have been normalized uh, by the number of parameters that are there in that particular model. So if you look at efficient net, corresponding to the number of millions of parameters it has, it gives you the best performance. So, and even this Google net that you see here is the next performing architecture. However, if you were to use Google net in your graphic card, so assume that you were using Titan XP NVIDIA graphic card, you would not be able to fit this Google net in a Titan XP card of, say, 8 GBs. However, you could fit efficient net and even achieve a better performance than that. Then the choice of the deep neural network architectures, you have to keep it optimal so as to ensure that you can train with a big enough batch size to achieve good generalization performance. Now, the very confusion that is out there within the public, and I should say the media also, that what truly is artificial intelligence and what truly is like machine learning and even deep learning, I should say. So these terms are, they are used as synonyms. And sometimes they are, in other cases, I should say, they are used as like discrete parallel advancements. Even industries, they take advantage of the trend to create hype and excitement. And they associate themselves by saying that we do AI and machine learning so as to increase their sales and revenue. So it is creating a lot of confusion out there. So if I were to separate these three different paradigms, then you could say that deep learning is a specific implementation of, because deep learning is nothing but one of the algorithms, which is nothing but neural nets with a large number of hidden layers. So it is essentially a machine learning algorithm. Similarly, machine learning is nothing but a subset of your artificial intelligence. If I define it more crisply, then you could say that machine learning is actually a branch of AI. It is actually one of the ways in which we expect to achieve smarter agents. So the idea is this machine learning relies on working with small to large data sets, and it examines and compares the data to find patterns and explores nuances, whereas AI, on the other hand, is actually, it's very vast in scope. So it refers to this broader idea where machines can execute tasks smartly. So, and deep learning is nothing but, you could say, a machine learning implementation with the large, with big neural networks. So, if you look at, say, 50 years ago, a chess playing program was considered as a form of AI. Since, a game theory along with like game playing strategies were the only strategies that a human brain could perform. And nowadays, if you look at this, playing a chess game is actually dull. and it is obsolete since it is like a part of every operating system out there. So I would say this term AI is actually aspirational. It is nothing but a moving target on those capabilities that humans possess, but which machines do not. So the goal is to make machines do as good as humans, and you have to make the machines smarter. So the idea is you have to, I mean, this particular domain includes a considerable measure of technology and the advances that we know of so far. So I don't know whether you have heard this or not. In 1997, there was this supercomputer built by IBM known as Deep Blue. So, this Deep Blue supercomputer they used to defeat the world chess champion, Gary Kasparov. So, this AI, this beautiful AI, it defeated the world chess champion in 1997. Also, very recently, you would have heard of like Google's DeepMind AlphaGo, which defeated Lee Sedol, who is nothing but one of the most, I would say, a prodigy who plays that game called as Go. It is also a board game, and this board game is much more complex than chess, and has, millions of times more number of possible combinations than I would say the game chess that you guys play. So Google actually achieved a significant landmark in 2016 by beating several Go players. Now, if you look at from the very beginning, since its inception, the industry has gone through many fluctuations. In the early decades, there was like so much hype surrounding the industry. People believed that human level AI was just around the corner. However, there were like so many undelivered assertions, which caused like a distress in the community. And along with that, uh, I mean, people started to, industries, they removed the fundings, and then came the AI winter period. But not so long ago, I would say a decade back or so, big data, predictive analytics, machine learning, they started gaining, a lot of popularity. Even in 2012, when neural networks made huge strides and they found their application in a large number of fields. So organizations have started making use of machine learning and deep learning for like advertising their products. The tasks which were impossible to do with like classical rule-based programming. Now, you could see that with deep learning, like speech and face recognition, image classification, natural language processing, they have taken like great leaps. Uh, and the three scientists that I showed you earlier, very recently in March 2019, they accepted the Turing Award, and we should be really proud that AI and ML is gaining like a lot of traction lately. So just to show you, how relevant AI is today, and even ML and deep learning. So this is this hype cycle chart, which is released by the agency Gartner. So you would see that. This chart actually represents, or you can say, it is divided into 5 different phases. So the very first phase that you see is the innovation trigger. So the innovation trigger actually represents a technology in its budding phase. So it has come into existence, and now more innovations and more research is going on. In the second phase, you see that the peak of inflated expectations is out there. So everybody is working on this particular area, and people are hyped, and they expect a lot out of this technology. Then comes the trough of disillusionment. So they realize that whatever assertions or dreams they thought of, or whatever expectations that they had, it was a disillusion. And right now, if you see, computer vision is going through a trough of disillusionment. Even you see machine learning, it is now in that phase. Thereafter, comes a slope of enlightenment. In this phase, the field starts gaining traction again. So if any you can say new advancement comes, it starts to gain popularity again. And if there are any insights, then the field starts getting more popular. And right now, only one field that you see, the GPU accelerators field, is in the plateau of productivity. You could say that this is one of those fields which is, I mean, very strong in the market and is doing very well commercially. So NVIDIA and other graphic card making companies, I mean, they are getting richer and richer because right now deep learning is very popular. So I just wanted to show you like what are the different technologies out there, where they stand. The color that you see for each technology, it is actually representing how much time it will take to reach this plateau of productivity. So if you look at computer vision and even machine learning, it will at least take 2 to 5 years to get into this plateau of productivity area where you could actually commercially utilize, I mean, different computer vision applications, even machine learning. Uh, so some of the applications, they are still commercially used, but I mean, they don't gain as much popularity like NVIDIA GPUs are gaining right now. So let me just show you a few applications uh, where machine learning is used, like in our day-to-day lives. So I mean, the landscape is very vast. So from medical diagnosis to education, to consumer finance, to I mean, to intelligence tools, to marketing. I mean, to detect security and surveillance, fraud detection, like gestural computing, where you would want to identify the mood of a person, if he is feeling pain or not, into robotics. So I mean, AI and machine learning, they are ever pervasive right now. So you see them on every platform nowadays. So just to give you an idea of like where you would see machine learning and in which areas it is more commonly used. Then I also want to talk about specific applications which you see nowadays. So one is like autonomous cars. You would have heard of Uber and Tesla getting into this driverless cars. So back in 2011 and 2013, I should say, that 3-4 year period, there, people came out with the idea of driverless cars, and they were pretty successful. But a couple of accidents happened, and now another field is out there, which is known as ethical AI. So there, they want to, actually emphasize on the fact that uh, AI should be done ethically, and it should have moral policies. So you do not want a driverless car to, to affect an human individual, right? So there is no. This research was stopped, and now again, people are still working on autonomous cars, but they are trying to improve the technology, but are still into this budding phase. But back in the days, it was actually, several states in the US had legalized it. Now, you would have heard that deep learning is in the headlines everywhere, from robotics, from these, say, navigation on external planets, to robots doing surgeries. Uh, deep learning doing medical diagnosis. Paths, you want to find a path, you want to assist disabled individuals. Deep learning was everywhere, and it is still everywhere. So just to show you a few applications of where deep learning is, very prominent. So this shows that the figure on the bottom is actually the input image, and the goal is to label each and every object that is out there and present in this image. So if you see that the cars, they are being labeled, the roads are being labeled, and how accurately it is done, the buildings and the sky, the windows, the fence, everything is labeled so accurately. And you could imagine that this scene labeling, how much it has improved from the early days. Now everybody must be using Siri, Alexa, or okay Google, even Xbox voice assistant. There are so many out there. You can actually speak, and they would be able to interpret what you are saying. You can, just speak. If you want to type an email, just speak, and you would see the text. so accurately written on the text board that you have. I mean, so much stride has been done in the area of natural language processing. And I would say that because like machine learning and AI, they are ever pervasive. So let's say if you do a search engine, if you use a search engine like Google and you search a query like what is the recipe to prepare a specific dish, so there it retrieves relevant documents. So that ranking that it is given to the articles that the search engine has retrieved involves the page ranking algorithm, which is nothing but a machine learning algorithm working in the background. If you have ever purchased any product online, so you see product recommendations. If you have ever been to Amazon, even when you watch YouTube videos, you get suggestions. If you watch movies on Netflix, I mean, recommendation systems are very popular nowadays. Similarly, if you are actually using Ola, Uber cabs, you use Google Maps for navigation. How does it analyze which is the best route? So that is done on the go. So this live, I would say, navigation is again involves a machine learning algorithm working in the background. Then you have say license plate readers. You have facial recognizers. I mean, so machine learning is like ever pervasive. Even when you use emails, uh, I mean, automatically the emails which are spam, they directly go to your spam folders on their own. Even if you think of your favorite area, you would see that machine learning is present there in one form or the another. So, I mean, if I summarize it, actually all these applications, they would look very diverse to you. But I mean, if I summarize them, they can be actually broadly categorized into a few different categories. And the algorithms which work on these categories, they are very few. Just there are tons of variants out there, and you could use any of those algorithms to formulate your problem in terms of these applications that you see. So, I mean, for all the tutors out there, if you are if you're teaching machine learning or AI, so I would show you certain applications that your students can make even without using a GPU, or if they have a say a fairly good or fairly decent graphic card, like 4 GB memory is there in their desktops or laptops, whatever they're using. So a few feasible applications. So assume that you are walking around and you see a garbage lying nearby. So you could think of this application where you just click the image of garbage. The application directly detects where is the garbage and sends the coordinate to, say, the municipal corporation. The corporation comes and picks it up, and there can be a feedback forum where you post these pictures. So that is how you could efficiently utilize I mean, deep learning or any classical machine learning algorithm. Another interesting application which came out like 5 years ago was if you look at daytime imagery from satellites. So you could actually predict how wealthy a region is, what is the GDP of that region, and all those things you could figure out by just looking at satellite imagery. Even by using nighttime imagery, people could figure out how wealthy a region is just by looking at the amount of lights, what the amount of illumination that was present in that given image. So such ideas are like ever pervasive, and they are utilized very efficiently. Some more applications on effective computing, like if you are given an image of an individual, you would want to predict the mood of that individual. So it could be done on an individual level or a group level. Other things are like we are living in this online teaching age. So I mean, students they come to the classrooms and they don't respond. So can you make assistant for the teachers where you would want to predict how engaged a student is? Can you make an automatic attendance system? I mean, can you do invigilation? Can you do online proctoring? So all those things, can be actually realized with the help of machine learning and deep learning nowadays. So you would have seen a rage very lately where people try to click selfie pictures. I mean, by standing on cliffs and dangerous heights. So can you actually predict the depth with the help of just an image? So is it safe to be there or not? So just I mean, a fancy way of having an application where you would like to take a safe selfie. Another thing would be, say, people suffering from dementia, or people who are, I mean, disabled in one sense or the another. Can you build an assistant? So, for example, say I want to know where my keys are, and I am a 75-year-old person. I don't remember where the keys are. So, if there is a assistant out there who can, like Siri or Alexa, so if you just ask the Alexa, where are my keys, and the assistant tells you back, oh, they are located on your table, go and collect them. So, can you build such assistants for the elderly? And you can say variants of these are already out there. You would have seen nowadays, like with the social distancing out there. I mean, as the simplest thing that you can do is, like, if a person is wearing masks or not, if he is wearing it properly or not. So all those things can be done very easily with the help of, I mean, deep learning based models. If you had some healthcare data, like if you had MRIs or X-rays, you would want to do some diagnostics. Like if you are having, say, brain MRIs, you want to predict whether there is a tumor or not. I mean, you can predict cancer tumors as well. So all those things can be done in real time, and you don't even really have to tell. I mean, you just have to feed in the image and the corresponding output that is out there. So for every, say, MRI image, if there is a tumor inside that image, you just have to tell that this image has a tumor, and a new image that doesn't. So you have to feed in just tons of these images, and the model can actually now work on unseen images if you train it efficiently. Similarly, you can have tracking applications from surveillance for, say, to prevent theft, like surveillance of your kids out there. I mean, uh, the real-time sports tracking activities like Hawkeye in cricket, say, in football, if it's an offside or not. So such things you could actually do in real time. You can also identify manufacturing defects, like if I show you an image of a product, you can tell me if there is a scratch or not. You don't have to do it manually. So just you can say camera sits there, and the footage is actually used by a deep learning model, and it can actually identify whether this product is foolproof or not. Now, another application which is right now implemented in Pinterest is that, suppose if I show you an image, can you tell me where I can buy the product which is there in that image? So that is another application that you could think of. Also, suppose, I mean, another thing is, like, if I show you an image, can you tell me what is there inside that given image? So write the corresponding text for an image. So such things can be easily implemented. So before I start with, I mean, what is predictive analysis? What are the different machine learning algorithms out there? I mean, what are the different categories? I would like to take a few questions. So if there are any, please let me know. I'm sorry, I will not be able to see the chats. If you have, I mean, please, you can unmute yourself and ask if there are any questions.
Hello, sir. Yeah, I'm
Hi,
Rita
ma'am.
Koshi from Bombay, Sardar Patel Institute of Technology. Yeah, so the session is very interesting, and we got to learn a lot. What I want to ask is, the sentiment analysis comes in which category of AI? And what are the latest advances in sentiment analysis?
Okay. I mean, should I tell you only the latest advancements, or how it was done prior as well?
Yeah, if you have time, I have no issue.
Sure. I can answer this question, like, I mean, very briefly for a couple of minutes. So
Yeah.
the idea is, I mean, so we are talking about text articles here. So assume that you are given a review of a product, so, and you want to analyze the polarity. So I mean, is it conveying a positive sentiment or a negative sentiment? You can actually also categorize it with the help of a rating. So how good that review is, whether you would want it to be rated with a score of, say, 1 or 5. So anything you could do with such applications. So what you need to do is, I mean, or I should say, the algorithms which were built, like I would say 15 to 20 years back, they used to, build around Bayesian modeling. So you used like Bayes theorem to identify what is the polarity of a given document. So it is from the probabilistic perspective. Do you know what Bayes theorem is?
Yeah, I have some idea.
Basically, you compute the prior probability and the posterior probability, and you determine. So suppose if I give you a document and I simply ask what is the probability that this document is rated with a score of 3, 4, or 5. So you estimate those individual probabilities, and whichever probability is the highest, you say that that is the corresponding rating or the corresponding category for that particular review. Now, there came a time where I mean, people started to use deep learning for text analytics. So I mean, so several I would say representations have been developed. I would recommend you to check out, like I mean, different representations like word2vec, glove modeling. I mean, there are several out there. So what you could do is you can feed in an input document and get a low dimensional representation of that document. And corresponding to that low dimensional representation, you can train a model and get a more efficient score. So this was done, I think, 5 to 7 years back. So there are a lot of embeddings out there, like Muse embedding is out there. So you can use that embedding to get a low dimensional representation, and again, using that representation, you can train a supervised learning model. And very lately, I mean, there are like developments, I should say, in the field of NLP, where they use spatial coherence. Basically, there is, I should say, have you heard of transformer architectures and attention architectures?
Not much.
So I would recommend you to go through those architectures. So these architectures are very prominent in the area of text processing, and they can be used to, I mean, to model sentiment analysis tasks more robustly than what was done like 5 years ago.
So transformer architecture is part of deep learning.
Yes. I mean, so you can say it's a specific kind of a deep learning architecture. So that is used, that can be used for natural language processing as well. You can look at transformers and even attention-based architectures.
Okay. Is it better to use NLP or deep learning for sentiment analysis?
It depends on what kind of infrastructure that you have. I mean, if you have a large amount of GPUs, you can go ahead with it, and I promise you that you can get, I mean, a much better accuracy in terms of the prediction scores that you want to, I mean, have for sentiments. And there would be a boost of around 15 to 20% approximately.
Yeah, so how exactly do we choose the algorithm? Like sentiment analysis can be done with in naive Bayes or with SVM or with
yes,
transformer architecture. Okay, transformer architecture, you need processing power and you get better performance. So should we not look at SVM and naive Bayes at all? Is that the way?
No. So see, when you write a paper, so suppose you have collected a data set where you want to do sentiment analysis, right?
Yeah.
So the very first thing that you have to look at is the size of the data set. If you recall, I discussed about what is the bottleneck in deep learning. the amount
Yes,
of
you
data
need a
that
lot
it
of data.
requires. Yes. So if you have, I would say, close to say 50K examples, 50,000 examples, even then I would say you should go for modeling with embeddings. So you can check out glove embedding, word-to-wake embedding. There are other embeddings out there like Muse as well. So
Yes.
just pass this text document to those embedding models. You will get a low dimensional representation, because if you use the original text representation, which you can further, I mean, transform to say bag of words or word count or whatever you want, that is, I would say, not much informative. So instead, using like pre-trained deep learning models to get robust low dimensional representations, and then using a SVM on top of it. So there you could get, a better performance. However, if
Okay.
you have like GPU power and a large amount of data, then I think you should go with transformers and attention-based architectures.
Okay. So transformer and attention models are available, what
Yes,
libraries?
so attention and transformer architectures, they are nothing but specific kinds of neural network based architecture. So you can get these implementations in either the TensorFlow framework or PyTorch framework or Keras framework. There would be several implementations out there. You can just check out GitHub, even do a simple
Okay, sir.
Google search, and you would get
Mhm. Oh.
several of these implementations.
Mhm. So
If
that
you
means
want,
nowadays this naive and is not used in sentiment analysis.
it is actually obsolete, if I'm being honest.
Okay. Mhm.
I mean, nobody uses that. You can
Okay.
say it is nothing but a baseline where
Mhm.
you would want to do at least that well.
Mhm. So SVM is also not used.
Uh, Not per se. You can use SVM on top of these low dimensional representations that you get from pre-trained deep learning models. That
Okay.
you can do.
So if
So classic,
I
yes.
ask, like, other than deep learning, assuming that the resources are not available, so if I don't want to use deep learning, which other algorithm would be good for sentiment analysis?
That's what I've been telling you. Like, you don't need to have GPU. What you
Mm-hmm.
can do is you can pick up any pre-trained model. So I'll give
Mm-hmm.
you one idea. So there is this glove model, GLOVE.
Yes, yes, I've heard.
So this model was trained on the Wikipedia corpus.
Uh-huh.
So Wikipedia is a huge data set, right?
Yes.
So what is done there is like two words which are semantically similar. So correspond, or rather, I should not say two words. So if two documents are semantically similar, they will get a representation which is very close to each other, which is very similar.
Hmm.
So basically, suppose you're feeding in a text document
Yes.
and you want a 100-dimensional representation.
Hmm.
So from that pre-trained model, you get that 100-dimensional representation. So now this 100-dimensional representation can be taken as an input, and the output you will have corresponding to, I mean, what was the sentiment of that particular document. So with that new representation, you can now train a model, and that, with the help of doing cross validation later on, you could
Okay.
estimate performance of your model.
Okay. Okay, sir.
Uh, yeah, thank you. Any other questions if anyone has? Okay, so let's move forward. So, one thing, people ask all the time is how machine learning is actually different from traditional programming. So the idea is, if you know what you want to do and you have collected the data for it, and corresponding to the input data, you know what is expected out of that data, what is the corresponding output. So in traditional programming, what you would do is you would write a program and you feed in the input data, and then based on that program, you would get the corresponding output. However, in the context of machine learning, what you do is you feed in the input data as well as the output data, and the model eventually comes out with an algorithm, or you can say a program, which can now work with unseen examples and do generalization and make decisions accordingly. So this is the very difference between traditional programming paradigm and the machine learning paradigm. Now, people ask like where you would do machine learning. So, I mean, I always say that there is no need to actually calculate simple interest or compound interest because you directly know the formula. So you would use machine learning only when you could say that where there are no, where there is no human expertise. For example, if you want to navigate on Mars, I mean, so obviously a human cannot go there. So you would want to have an algorithm for path planning where a robot can navigate. Similarly, whenever for a task, it is difficult to explain how humans perceive that task or how humans do that task. For example, speech recognition. How do humans recognize? I mean, speech I mean, requires a I would say requires very intricate level of understanding and complex representations. So there, I mean, one can recommend machine learning instead of writing traditional programs. Similarly, when the solutions they change over time, for example, stock market predictions like financial modeling, so there machine learning can be preferred. More specific cases like you want to do identify an individual, if you want to do recognition, so example like biometrics. Now, a key thing to note is that whenever we want to do machine learning, we need to have a lot of data. So as I mean, in the advent of World Wide Web, the age we are living in, data is actually cheap and abundant. But you would have to pre-process this data, and you would have to get, I would say, informative data, and getting knowledge out of this data is actually expensive and scarce. So, I mean, I would summarize these things more in detail as we move forward. So, the idea is, I mean, if I summarize the different things that we could do with machine learning, I mean, all the approaches out there, they can be traditionally divided into these three broad categories. So one category is like where you give the example inputs and the desired outputs. So and the goal is to learn a rule, or you can say learn a mapping between inputs and outputs. So that field is called as supervised learning. So for example, so I'll be discussing the examples of each of these in the subsequent slides. So in unsupervised learning, what you do is, so I will just give you examples, and I will ask you what kind of structure is there in these examples. So that comes under unsupervised learning. Similarly, another paradigm is reinforcement learning, where you would want to build an agent which actually interacts with the dynamic environment with a goal in mind. So for example, you have, suppose you want to play a game, and so you want to take a certain decision based on how your opponent is reacting. So your agent is navigating that problem space, and you can say the reinforcement learning model is providing feedback. You can say it provides a positive feedback if you take a step towards the goal, and if you are moving away, then it gives you a negative feedback. So the goal is to you can say maximize the reward or the feedback or the positive feedback. So that is the idea of reinforcement learning. We'll discuss the applications of each of those in the subsequent slides. Now, if you want to formally define machine learning, then I mean, Tom Mitchell is a very world-renowned computer scientist currently working in Carnegie Mellon. So he said that a program is said to learn from experience E with respect to a certain class T. And correspondingly, it wants to do well with respect to a performance measure P. Now, the idea is, suppose, rather let me just give you examples which makes it more clear to you. So assume that you are playing checkers. Now, the task is the playing checkers here. You want to become good at checkers. Now, what could be the performance metric? So suppose you played a game against an arbitrary opponent and you won. So if you played 100 games, the number of games that you won would be a performance metric. Okay, and the experience is the number of games that you played against an opponent or against yourself to make the model better. So that is nothing but experience. So experience, you can say, that is the data that you have to train the model. Performance metric P is some metric which tells you how good you are doing. So if you want to compare two models, this metric is what you will use to compare two different models. And the task T is you can say the work that you intend to do. So I'll just take another example. So suppose look at the last example. So assume that you want to build a spam classifier. So if email is benign or it is legitimate, oh sorry, if it's a benign email or a spam email. So now the idea is you have a training set and you build a model. Now you pass some unseen examples and you see how many of them it got correctly classified as spam and how many of them were actually legitimate. So that would be nothing but your performance metric. And the experience is nothing but the training set that you provided to build the model. So with this formal definition, every you can say every machine learning algorithm can be characterized with this the task T, the performance metric P, and the experience E. Now, if I characterize every algorithm, so there are three important, I should say, features of each algorithm. Three important characteristics or components, you should say. Now, if you are familiar with machine learning domain, then you would know that there are thousands of algorithms out there. Now, if I summarize, then each algorithm has a representational component where you want to describe the set of assumptions, and you would want to model how the input is related to your output. The second thing is you would want to evaluate this model with a performance metric. So if I gave you two different algorithms, two different representations, how would you evaluate which model is doing better? So this is done. So there has to be some evaluation metric. And the third thing is optimization. So with this optimization, you would want to find the optimal performance corresponding to an algorithm. So you would want to tune the parameters and the hyperparameters corresponding to the algorithm. So so I would say, in summary, you would write an optimization algorithm and you would want to minimize or maximize that optimization algorithm and try to achieve the optimal parameters. So these three components form an algorithm, and we would discuss, I mean, what kinds of representations, what kinds of different algorithms are out there, what are the different evaluation metrics, what are the different optimization approaches out there. So let me just give you an idea. So representation is nothing but you can say a way to correlate between your inputs and outputs. So these are the some of the algorithms that model your inputs, like decision trees, k-nearest neighbors, Bayesian networks, neural networks, support vector machines, ensemble learning approaches, bagging and boosting, different clustering algorithms. So these are some of the representational techniques out there that you could use to model your inputs. Now, we discussed that. So suppose you are given a training set. Now, how do I assess that how my model is doing? So if I give you a data set, what is essentially done is you partition this data set into train and test, and then you report. So what you do is you optimize the performance on the train set. If there are any parameters that you want to tune, then you create a validation set out of the train set, and then you tune the parameters using this validation set. So whatever best parameters that you obtain using the validation set with that model. So suppose I learned a model with the help of this validation set. So this model is then applied to your test set, and then you report the accuracy. However, in the when you write research papers, you cannot simply say that the performance is based on a single test set. So essentially, what we have to do is we have to do you can say an iterative way of testing, where we have to consider multiple you can say multiple test sets to designate the approximate performance of a model. Now, the idea of why would you refute that if you use a single test set, I mean, the performance model is not sufficient. So the idea is, if you use a single test set, then that performance is biased towards this test set. There is a chance that there exists another test set where the performance can be poor. So what you could do is you could create multiple test sets, and based on the average performance across these test sets, you can report the performance. So you can report like the mean accuracy and the standard deviation, and corresponding to those two metrics, you can compare two or more models. And if your average performance is better than another model, then you could essentially say that, yes, because my performance was better over several test cases or over several test sets, then only I could say that my model is doing better on average. So that is how it is done in, in research articles. So I would suggest you guys to read about what is k-fold cross-validation. So since there is limited time, I am not going to cover this in detail, but the idea is very simple. So here you have like multiple iterations. In each iteration, the test set is different, and you report the average performance over these multiple iterations. Now, depending on the type of task that you are doing. So suppose you were trying to identify, say, if a particular email is spam email or not. So then if I give you 100 documents, so on an average, if you tell me that there are 60 documents which I got correctly classified as spam, then your accuracy is 60%. However, if I want you to predict, suppose what is the weather today, and suppose if you predict the weather to be, say, 30 degrees Celsius, but it is, say, 40 degrees Celsius, then one metric could be the difference between these two values. So depending on the task that you have, you can have several evaluation metrics. So these are some of the evaluation metrics that you would be using for different kinds of tasks. Now, when you write optimizations for these different algorithms, there are, these optimizations, they are of different types. So depending on the type of the optimizations, you have different optimization solvers, or you can say you have different techniques to solve those particular optimizations to get to the optimal values. So depending on whether your optimization is convex or non-convex, depending on whether it's constrained optimization, I've listed out a few ways to solve those optimizations. Now, in your machine learning you can say domain, you would come across these two methods very often. You would come across gradient descent and Hessian based methods, quite regularly. So if you're not well versed with these, you can, they will be discussed in the subsequent sessions. So meanwhile, I would recommend you guys go through these variants. Okay. So just does anyone has any question?
Yeah, sir, one question. What do you mean by the convex optimization?
Okay, so convex optimization.
I have heard about gradient descent and all that. So what exactly is convex optimization?
So convex optimization deals with convex functions. So let me just give you a very brief idea. So assume that you have, say, a performance metric, and this is the parameter that you want to estimate. So suppose this is the, sorry. One second. Okay, so suppose this is the corresponding variable, or the variable that you want to estimate. Now, suppose this function looks like, say, a parabola. Okay. Now, I want to minimize this function fx. So if I want to minimize this function fx, the optimal value, or you can say, because I want to minimize this function, so this is the least value that exists for this function. And corresponding to this value, I actually want to know what is this value of x where you get this optimal value of the least value for fx. So convex functions are those functions where you take, say, 2 points. I'm just going to give you the definition in a layman language. So if you take any 2 points on this convex function, and if you draw a line between these 2 points, then the line should be above than the, the line should be above, the line should be above than the curve of, then the, you can say, so suppose if this point is A and if this point is B, so the corresponding to all points in this AB, so this line that is out there should be above the surface of all points that come between FA and FB. So do you get the idea?
All points. The last sentence I didn't get.
So the idea is, so if you join these 2 points, so you will get a line between A and B, right?
Yeah.
So you have a certain value of FA here and certain value of FB here.
Yeah.
Right. So
yeah.
all the values that are, so all the values that are on this curve.
Yeah.
So they should be below this particular line. So that is the idea for what a convex function is. So let me just give you one non-convex function, so it will be easier to understand. So assume that this is the function. So if I take any 2 points, like say 1 point is this one and 1 point is this one, if I join a line, then the values between these two, A and B, so this is lying upwards, no? So the idea behind a convex function is you would always get one minima, one optimal minima would be there. That is why convex functions are preferred.
That is, it has a global minima.
It has a global minima. I mean, for you to check if a function is a convex function or not, you can directly take the double derivative, and if the double derivative is greater than equal to, is positive, then you can say that that function is convex. So I'll just tell you. So this function is nothing but x square, some form of x square, some ax square. So if a is positive, then 2a would be the double differentiator.
Yes.
So because 2a is always positive, given that a is positive, so because the double derivative is positive, so this function would always be convex.
Okay.
So the idea is, in optimization algorithms, whenever you write optimizations, you would try to make it convex, so you can get that one global minima. And if there are multiple local minimas, then you have to start from multiple starting points and then get the local minimas. And whichever is the local minima, you have to identify the least local minima amongst all. I hope this answers your question.
Yeah, thank you, sir.
Now, okay, I thought of asking a question. So, suppose, so the very first question that comes to mind is like, why do we want to do predictive analysis? Why people think that, we want to model relationships between 2 different features. So, so let me just show you a particular data set. So assume that you are given a list of, I think there are correspondingly 60 to 80 students here. And each row is representing 1 student. What you have done is you have recorded the, you can say the grading score out of 100, grade point average of a particular student, and the number of hours that the student spends online. Okay. So I want to model this relationship. Suppose if I tell you how much is the grade point average, can you tell me what is the number of hours that the student spends online? So I'll give you this data set. So just let me show you a better representation. So this is nothing but a scatter plot. So with this scatter plot, you see that each data point is representing a particular student. So this data point represents that this particular student spends close to, say, 57. This student has a 57 GPA and spends close to 8 hours. So if I ask you in general, Can you tell me if there is a relationship between GPA and time online? Can you guys conclude something from this very data set? Can you make certain arguments whether a student's GPA is dependent on the time that he spends online? Don't think intuitively, but by looking at this data set, can you make a general argument? So this is a question to all of you. You can unmute yourself and think about it.
Please repeat the question, sir.
So what is
GPA?
given in GPA is nothing but the you can say the performance of a student out of 100, and on the
Yes.
y-axis is you have the number of hours, the
Time.
the time spent by, say, the student on internet.
Okay.
So what I want to
So,
know is, do you think that there is a relationship between this score of the student and the time he spends online? Not by
okay.
intuitively thinking, but by just looking at this data set. Essentially,
The lesser time they spend online, and the more GPA, I think.
I mean,
According
are
to
you
the data
saying that intuitively? Because
according to the data set.
why do you say that? I mean, can you give me? So let me just give you.
Yeah.
So what you said
The
was,
time online is low. There are more points.
no, I would say that here
it
there
is
are. I mean, if you
independent,
say
sir.
it is independent
It is
actually. Yeah,
okay.
it is independent.
Because
Yeah,
the
there is
variance,
actually.
my way of looking was the variance of time data is less when compared to the uh, uh, GPA, and the principal component is what. Is that the right way of?
Yes, you could say that.
Yes, sir.
So the idea is so even so actually there is no relationship between GPA and time online if you look at the students on average. So there are students who spend less time online and they still have good GPA, and even also there are I mean a large number of students, they spend a large amount of time and they still have a good GPA. So there is, and you could say vice versa, and a combination of two. So if you draw the quadrants, there would be 4 quadrants: low GPA, more amount of time; low GPA, low amount of time. So there would be 4 distinct values, and in each of those quadrants, there is almost equal. I mean, equal number of students present there. Now, such kinds of questions are actually very interesting, and we would want to know. We would want so the very first question that you guys answered was whether there is a relationship or not. Now, what if I ask you? What if I ask you? So suppose that I give you this. So suppose that. Just give me 1 second. Yeah. So suppose that if I draw a line. So if I draw a line, so this is nothing but a linear line which represents the relationship between GPA and time online. So essentially, this line can be represented as time online equals GPA plus some constant. This constant is nothing but, sorry, this constant is, so if you remember, the equation of any line can be written as y equals to mx plus b, where m is the slope and b is the intercept. So if I simply write this, time online can be represented as alpha times some coefficient times the GPA plus some constant. Now this concept is nothing but the intercept, and this alpha is nothing but the slope. So if I tell you, say this is one line which is given to you. Now if I give you a certain GPA, so suppose if I tell you what is the corresponding value when the student has, say, 83 GPA, how much time it spends online. So what you will do is you will say alpha times 83 plus some constant, whichever is given to you, and you can compute the time that he spends online. So a simple prediction to do this would be, so you assume that the relationship between GPA and time online is actually linear. And whatever the coefficients of this line are, the slope and the intercept, you can actually determine what is the amount of time a student spends online. So that is how you can make predictions. Now, the question is, how do I determine the optimal values of this alpha and this constant, this M and B? Because if you change the values of M and B, you can get this line, you can even get this line, you can even get this line. I mean, there are several ways you can get different types of lines basically. So the idea is, how do I determine this efficient line? So I mean, the very first algorithm that you guys actually study in machine learning is known as linear regression. So there you will try to model the relationship as linear, and then you would make an optimization algorithm and try to find out these optimal parameters M and B. So that is the essential idea. I mean, so you assume the relationship to be linear. What if it was non-linear? So you will I mean, pick up a particular polynomial equation to model this time online and GPA, and from there you would determine the optimal coefficients using certain optimizations. And whenever you have achieved those optimal coefficients, you can then use those coefficients, substitute them in the equation, and get the corresponding output for any value. So that is the basic idea of doing machine learning. Okay. So let's actually discuss what is supervised learning. What is the standard paradigm? So in the initial figure, we were trying to relate, say, what is the amount of number of hours that a student spends online, and correspondingly, we were trying to model what is the GPA for that. What is the GPA for that student? So if you are trying to model a particular feature which is real valued, so in this given example, say if I give you say an image of a food, and I want to predict what is the number of calories in that given food, in that particular dish. So this kind of task is actually known as a regression task, because the number of calories, you can say the output variable that I'm trying to model is real valued. Similarly, another example could be age estimation. Given an image, you would want to identify the age of the individual, because age is a real number. So you can say that this particular setting belongs to the regression scenario. Now, considering the same task that we did earlier, can you think of any algorithm? So suppose I ask you, corresponding to say this, or rather say this data point, or let me just give me 1 second now. So corresponding to this point, can you tell me what is the amount of hours that the student spends online? So I have asked you that if the grade point average of a student is say 73, can you tell me what could be the expected number of hours that the student spends online? Can you make some estimate? It's a simple question to everyone. So you have this data set with you. Now, just by looking at this data set, you could see that there are people who have closer to 72 or 73 GPA, even 75 GPA is out there, even 70 GPA is out there. Can you utilize this information to predict the number of hours that the student spends online? So the hint is, can you just look at the nearest neighbor?
Okay. Okay.
You were saying something, right?
We cannot predict. That is what, sir.
No, see, the goal is to estimate. I'm not asking you to give me the accurate value. I'm asking
GP,
to make a prediction.
Yes. Okay. So by nearest neighbor concept, yes.
Yes. So the idea is, so suppose if I make a guess somewhere close to here, which is I've denoted in green. Will that be a good enough estimate? Basically, the number of hours that the student spends online is close to say 1.1.
Yes, sir. Yes, sir. Definitely.
Because what I have seen,
Yeah.
what I can see is that there are two neighbors which are next to this point, which almost have the same amount of hours that the student spends online. So the idea is, you look at the nearest neighbors. Here, K tells you how many neighbors that you want to look at.
Yes, sir.
So K is telling you how many neighbors you want to look at. You can look at 1, you can look at 2, you can look at 3, and then maybe take an average of those neighbors and report that particular value as the estimated value.
Okay.
So basically, because we want to do predictions, I would want to know how well am I doing, right? So suppose if I predict the value as 30, but it was say 35, one would be say you take the difference between the two and report the absolute value. And if you were doing it over say 100 samples, so suppose in another sample the actual value was 40, but you predicted as 32. So you would sum it up over all the samples, and then you would take an average of, say, if there were n samples, you would take an average and you would divide the entire sum by 1 by n. So this is nothing but mean absolute error. Similarly, you can take the differences between the squared values. So that would be nothing but mean squared error. So these are some of the metrics that you could use with a regression. Now I'll just skip these things over. I will share the slides. You can go through these slides. These are well explained. Now I just want to cover up the paradigms. Another paradigm is classification, where instead of predicting a real value, suppose I want to predict to which category a particular input belongs. So for example, in this particular figure on the right, on the top right, you see that if I give you an image and I ask you which digit is there inside that given image, it could be an image with digit 0, it could be an image with digit 1. So there are 10 possible categories. So you would answer corresponding to which image is there in that, which digit is there in that given image. So because there are 10 categories, the output is not real valued. It is just those 10 categories out there. So this kind of task is known as classification. So I'm just going to skip a few of these things. Then I'll just show you another paradigm, which is known as unsupervised learning. So the idea here is you want to, so suppose if you are given an unlabeled data set. So suppose the data set that you look on the right is an unlabeled data set, and I ask you how many groups are there. So just by looking at it, you can tell me that there are 2 groups. So which I have labeled as red and blue. So if you are given any representation, you could be asked to identify the number of groups to cluster the different inputs that you have. Another application could be, say, recommendation systems. So if I give you a set of movies that the user has watched, can you identify new movies which he would likely want to see? So that is also a type of unsupervised learning. Okay, so let me just show you a few example applications, because we are almost we are almost about at a close. We are close to like 12:30. It is like time is already over. I just want to show you a few things. So if you are working in this machine learning area, I just want to show
Sir,
you
one
a few.
small question, sir.
Yes, ma'am.
Yeah, just now you told a nice problem that looking at the earlier history of his movies look through, we can predict as an unsupervised.
It's an unsupervised. So what you will do is you can
Okay.
actually look at other users. So you can find so you have a collection of users, right? You know the history of other users as well.
Okay.
So you identify another user which resembles him, and then from his history you recommend him something. So this is, I am giving you a very layman kind of an algorithm. You can actually improve upon it.
Yes.
So this field is known as collaborative filtering.
This type of collaboratively knowing
Yes,
from the
yes.
other users and predicting.
Yes, yes,
Okay,
yes. There are actually
fine,
different
sir.
optimization algorithms out there. You can look it up. I mean, this field is more commonly known as recommendation systems, and the algorithm that you
Okay,
use here is collaborative filtering.
okay, sir. Thank you, sir. Okay.
Yeah. So just let me. I just want to show you a few applications which might inspire you to do a lot of stuff later on. So if you are in the deep learning domain, if you want to be in this machine learning domain, in the last decade, I told you guys, I mean, this generative adversarial networks is the most, I would say, the most promising research that has come out in the last decade. So the figure, the image of the person that you see is Ian Goodfellow. If you are in this machine learning domain and if you don't know him, then go read about him. So this guy created generative adversarial networks. It is a kind of a deep neural network which can do a lot of things. Let me just show you a few things which this architecture can do. So this architecture, so one of the problems that we have with deep learning networks is that we require a large amount of data. So I mean, to just remove that bottleneck, you can actually create good quality synthetic images by using these architectures. So one of the you can say purpose of using GANs is to create synthetic images. So all these images that you see here, they are synthetic. I mean, they are not real world images. And you see that the clarity that is there in these images. Now, I want to ask you a question. So suppose you are seeing a few, people images out there, right? Can you guys tell me how many of them are real and how many of them are synthetic? Just by looking at this figure, some of them could be real, some of them could be fake. I just want to ask you guys, how many do you think are actually real? How many are fake?
Only one is real, sir. Two.
Which one do you think are real?
A lady in the top row, third,
Okay.
1, 3.
Okay.
And
And rest.
the beside a person also. The rest
Okay.
are.
Rest are okay. What about the second person on the second row? The male in the second row.
Yes, sir. Might be, sir.
Okay. Okay.
No, not
Let
if.
me.
Yeah.
Okay. Let me just give you the answer to this. All the people that you see here are fake. They do not exist in real world. So just to show you how much clarity you can get with such architectures, this generative adversarial network architecture, it is actually a variant of generative adversarial network, progressive growing GAN. This research was done by NVIDIA, I think 2 to 3 years back. So you see, so these images are synthetic images created from the faces of celebrities. So there is a celebrity dataset known as Celeb-A dataset, which you can use to train your model. And this generative adversarial network, it actually synthesizes new images, and these are those new images that you generate from celebrity dataset. I just want to show you a few more pictures. What about these people? Do you think they are fake?
At least two are. The bottom row is real, sir. I feel.
Actually, all these are fake.
Fake. Okay.
Yeah. So just to give you an idea of how good quality images you can actually produce, I mean, it is even hard for humans to distinguish. So nowadays there is a field, research field, identifying deep fakes.
Okay. Oh.
So this field is getting very popular. So you would have seen several videos on social media platforms out there which are not real, but they seem so real.
Okay.
I mean, Trump speaking something, Modi singing songs.
Okay.
I mean, so such you can say media. I mean, you can
Sir,
say items. Yes.
one thing I feel more willing to know, interesting to know, what is that in the deep fakes? What is the intuitiveness that they will search for this false and the true images?
What
I
is?
mean, image processing. What is that these deep fake image algorithms are based on?
Okay. Okay.
To
So I just.
classify just 1 point.
Okay.
Yeah.
Okay. I'll just give you an idea. So
Okay.
these networks utilize game theory. So
Game theory.
the idea is there are two networks. on one network you feed in real images,
Okay.
and in another network you feed in some noisy data. It could be any noisy data. Okay, so this
Okay.
second network is actually trying to synthesize real looking images from noisy
Mm-hmm.
data. Okay, so suppose there are two networks. So here you feed in real images, and here you are feeding some noisy data. But this
Mm-hmm.
network is trying to synthesize real images or real looking images.
Mm-hmm.
So if there is another network out there, which I call this as a discriminator network.
Okay.
So this network is actually trying to discriminate
Okay.
between the output
Real
of these images and the output of noisy images. And if you can fool this network,
Okay.
basically the images that this network synthesizes,
Okay.
if they are real looking, and if they can fool this the output of real network,
Mm-hmm.
so then you can say the images that you are going to get, they would be very good looking images. Now there are a lot of intricacies for training this network.
Okay.
Even though this architecture might look very simple, there are a lot of intricacies to train this network,
Yes.
and it requires a lot of input data as well. It is not that straight. I mean, it is not that straightforward. I've just given you an intuition of how the architecture is. This is a basic GAN architecture where two networks are getting discriminated by another network, and the goal is to you can say, if this is the generator network, you are trying that this generator network should be able to fool the discriminator network, and if it is able to do so, then you can say that you are now at a point where you can generate good looking images. The training part is actually very intricate. I cannot explain it in like 2 to 3
Yes. Yes.
minutes.
Okay, sir.
So
Thank
just
you.
to give you a fair idea of how
Yes.
synthesis is done. Okay,
Okay.
let me just show you a
Yes.
few other applications which are very mesmerizing. Okay, so suppose you want to transfer the background of one image onto another. So that is now possible as well. This field is also known as image blending. So basically you see that this image is the original photo, and you would want to transfer the landscape of the middle image, the background of the middle image, to this to the image on the left. So this is what you will get. See, such good blending is there in figure 2 and figure 3. So this is another very interesting example of neural image transfer. Another thing is that suppose if you want to have suppose if you have an image of your family, and you would want to get it painted, but the painting should be in a style where, suppose famous painters used to paint. So suppose Da Vinci, you collected the paintings of Da Vinci, and now if I show a new image, the model should paint this input image with the flavor of Da Vinci, with the way Da Vinci painted. So that is also possible. So just to show you that if you give a reference image and provide the original image which you want to get painted as, so that you can also do. So another application of style transfer. You can generate synthetic anime characters from these neural networks. You can do image colorization. You can bring back your old photos to life. If you have some gray colored photos, you can actually bring those to life. Another application of generative adversarial networks. See how beautiful this architecture is, and how well it is doing. It is bringing this old photo of Albert Einstein back to life. So you can see the intricacies, the details. So D-Aldify is the name of the GAN architecture. If you want to look at, you can also color sketches. So this is the input, and this is how the output would look like. You can also, so if you give me a text image, or even if you give me some text, I can generate the corresponding image. So suppose if I type the small bird has a red head with feathers that fade from red to gray from head to tail. So this is how the bird images are being generated. So you just give in the text as the input. However, you can generate the corresponding output as an image. So I just want you guys to visualize what kind of world that we are living in. You can actually tell what to draw and where. So suppose if you want to, in the very first thing, you want to draw a blackboard, but at this position. So this is how the generated images would look like. So I mean, clothing translation, you would see that nowadays people, if you buy, suppose your sunglasses or lenses from Lenskart or something, you can actually try the frames virtually. So also there are several, you can say, commercial websites where if a particular product is given, you can try it virtually by uploading your image. So this is known as clothing translation. This is image super resolution. You can actually increase the resolution of, I mean, low resolution images. Similarly, if you have an occluded image, you can generate those images back. So this is actually used in security. So you can transfer, I mean, different animals, I mean, styles of different animals. Just to, I mean, show you, I mean, how well the applications are. I just want to show you one more. Yeah. So you can actually predict, I mean, what an individual is going to do by, I mean, right now, I mean, sports analysis is a big market. So when they want to identify which player is going to be successful, because companies like Nike and Adidas, they want to sponsor these athletes. So they want to know whether this athlete is going to become a, I mean, a prominent player in the future or not. So they do video predictions on those athletes and see how they will progress in time. So I mean, another good thing to look at. So this is it from my side. If you have any questions, please let me know. I understand that I could not cover, I mean, some of the topics. I mean, I tried to cover as much as I could in this limited time. But yes, I do have another session tomorrow. So I'll cover the rest of the topics there. Yeah.
Sir, this virtual trial and all that you showed, that is all applications of GAN?
Yes, these are applications of GAN only.
For such kind of applications, how do we measure the accuracy?
Okay, so usually this is done by using a human expert. I mean, the human expert would be there, and if the synthesized image is visually correct, or you can say visually appealing, if you cannot really differentiate whether if it's a, I mean, I should say whether that generated image has flaws or not. So then you would see that you can say that, okay, the generated image is good enough.
So if we are like for virtual trial for say eye spectacle frame or something like that. So if we are trying with say 50 images, then for each image we say what is the percentage of accuracy, or for all the 50 images we say
Yes,
the
yes.
accuracy.
Yeah, actually, there are performance metrics out there, I mean, in this field as well. You can actually measure the quality of an image, how smooth the image is, how the pixels are transitioning from, I mean, from one, how the transition is happening from one pixel to the other. You can check out, there are different metrics out there in the literature that can help you identify the quality of an image. So if the quality, so you would have seen sound to noise ratio, PSNR value. Do you, I mean, this metric was used way back, I mean, in 2000. So that is also one metric that you could use.
Sir, one question, sir. For any,
Yes.
sir, for any simple application of this GNANs, if I want to do, what is the minimum system setup requirement, sir?
Okay, so it depends.
Yeah,
Okay, so you please tell me the application that you want to build.
No, for a student project, I want to think about something. What you told about the.
So okay,
yes.
so suppose you want to generate low resolution images. Okay.
Okay.
So if I give you say a data set of cycles, you want to generate new cycle images. The size of the images, say 32 cross 32, which is very small.
Okay.
So there you could do it in I think 6 gigabytes of GPU. Even lesser than that.
Okay, 6
6
gigabytes.
GB, 4 GB of GPU would be enough to do this.
Okay.
Actually, you have to pick up a smaller architecture,
Okay, sir.
and then you could use those those architectures to build a GAN. Basically, the three networks that I showed you, one real network, the other noisy network, the generator network, which tries to synthesize new images, and the discriminator network. You can replace these three networks with with state-of-the-art real-world architectures out there.
Okay.
Basically, there are several established architectures that you could replace with.
Okay.
So, I think if the image size is small enough,
Yes.
and I think you would be able to do it in 4 to 6 gigabytes of RAM. Not much is required. But if you want to synthesize those real HD images that I showed you of
Yes.
celebrities,
Yes.
then it would require at least 12 to 24 gigabytes of RAM.
Okay. For conceptual understanding, to go with the small would be
yes. You can certainly do it. Yes. Yes, you can certainly do it. I think you can buy a system in your institute with like 8 gigabytes of Titan XP comes at a very reasonable price. You can, because you're an instructor, right? So what you can
Yes.
do is you can apply to NVIDIA. There is they provide free GPUs to instructors.
Okay. Yes, sir.
They have this facility. You can write to NVIDIA. You can search on Google.
Yes,
What is the procedure? I remember that my advisor used to do it every year or so. He has like 4 to 6 NVIDIA GPUs sponsored by them.
Okay, that means
So you can also do
mean
it.
to say cloud space they give something like this, sir? They give NVIDIA they give the cloud
GPUs.
space some GPUs.
No. They will give you real hardware. It will be shipped to you.
Oh, okay.
Yes. So what happens is, so every time they come up with a newer GPU, they provide these GPUs as beta testers to academicians and researchers.
Nice information, sir. Okay, sir. Thank you.
Yeah, you can do that. Yeah.
Institute is there. I heard in one of the seminars of NVIDIA Deep Learning Institute. DLI.
I'm sorry, I can't hear you. There is so much noise.
Okay, sir. The Deep Learning Institute of NVIDIA, sir. Are you able to hear, sir?
I can hear that.
Yeah.
I'm not sure of. I haven't seen that page very recently, but
Okay.
I recall that my advisor used to get it every year. Since the last 4 years, he has been getting it.
Okay, sir. Thank you.
You can actually find the link on by doing a simple Google search. You'll be able to find it.
True, sir. Okay, sir. Fine, sir. Thank you so much.
Okay. Yeah.
Thank you. Okay, sir.
I welcome other questions. Yeah, please. Please go ahead.
Yeah, Dr. Sanathan.
Yes, sir.
I think, you can invite 1 or 2 questions and we can formally conclude.
Okay, sir.
Hello.
Yes, sir.
Yeah, sir. Dr. Paresh Khanna here, sir. Good afternoon, sir.
Good afternoon.
Sir, I just want to know about the type of research projects that can be assigned to the students, like master students or PhD students in for the computer science, especially for the deep learning. Can I have that type of links or the sites that we can use?
Yeah, sure. Just look at these projects. Which I showed you, which I discussed here. I'll share these slides. There is enough information in these slides. You can assign even PhD
I already
level
gone
projects
through.
here.
I already gone through a chat message, but I didn't get a reply for that. So
I'm really sorry. I can't
no
see
problem. Sir,
chat
but,
box here.
not a worry. I just listen in the midwell. You already told that you are not going to check that. Not an issue, sir. You can, if you are going to check it, and if you're going to reply for that, that is fine. Otherwise, we are just thinking for, like, at the starting of the session, you mentioned the few YouTube channels as well as
Yeah, sure, sure. I'll
applications.
share
Yeah,
these
I
slides with
gone through
you.
that way also, but I
Okay.
unfortunately I am not able to write down that part. So if you are going
No,
to
no, no,
share
no
the
issues.
slides, then
Yeah, I'll do that. Yeah, you already
that
have my email ID here, so you can
yeah,
always email me, and yeah, I'll certainly respond.
no, not an issue. Thank you very much, sir.
Yeah, thanks. Any other question? Okay, guys. I think I should summarize. So we actually discussed how AI, DL, and ML differ. Often these terms are used interchangeably, but that's a misnomer. These fields are very different. We discussed a few domain, uh, I would say a few algorithms for predictive analysis. I showed you a couple of latest developments. Now, I'm really sorry that I couldn't do justice to this, 2-hour session, because, there was a lot to cover. Uh, However, when we meet for the next session, I ensure you that the material for even this session, I would cover very quickly. So that's it from my side. Thank you guys for listening. And if you want to interact with me, if you want to email me, I'll be available on this email ID. So thank you guys. Stay safe and take care. Bye-bye.
Yeah, thank you, Dr. Sanathan. You gave a wonderful lecture on this introductory programming. And probably we can formally conclude this particular session. And by 1:45, the session is going to open. And from 2 o'clock, we are going to have the second session by Dr. Neha Bharil from the same university. So thank you all for your okay. Thank you all.
Thank you guys. Take care. Bye.